All right, so let's look at the electric field at a point along the axis of a rod of charge Q. So we're looking at basically a one-dimensional charge distribution. It's just got a length. Everything has the same height and depth, so we're just going to treat it as a 1D object. So we've got charges that are uniformly distributed, right, along this bar, and that means a couple of things. It means that any length of this bar that I cut should have a ratio of Q over L for however much charge is in that section divided by the length of that section. So what I want to do to find the electric field here, a point P that's a distance D away from the edge of the bar, I'm going to go ahead and cut this thing into a little tiny length of dx. Okay? And that dx, that one little charge dq, if I want to find its contribution to the electric field over here, then I need to know how far away from point P is it. Okay, so the first tip that I'm going to give you is I'm going to say, when we want to find the electric field due to a uniform charge distribution, always put your coordinate system right here. Put the origin at the point P, okay? So it doesn't look like we have to look at anything in the y direction because every charge here on this bar is along the x-axis, and that means it will contribute an electric field in the x direction, okay? So I've got my origin right here. So then I would say the distance from this little tiny charge to the point P, we're going to call that x. And the reason we're calling it x is because every little charge has a different distance away. So that guy right there is our variable that is changing for every little charge that we look at. It has a different distance to point P. Okay? So in order to find the electric field at point P, that is EP, then we need to add up the contribution from each of the little charges. So those are little tiny DEs, little tiny electric fields from each charge. Right? We're going to integrate that from 0 to the total electric field at point P. Right? So what we're going to do then on this side is, well, add up the contribution from every little tiny charge dq all over, well, kq over r squared. Right? So here the contribution from a point charge, kq over r squared. Well, the distance from each charge to the point P is just going to be x. So we have k dq over x squared. Okay, great. But again, the moment I write down that integral, I notice that I have an issue because my small factor is q, but my variable is x. So I need to do a change here. I need some way to match those two. And I'm going to get that through the charge density. The charge density lambda, charge density, says that for a uniform one-dimensional bar, any length that I cut, the charge to length should have the same ratio, right? So for this little tiny length that I cut that was dx, the ratio of dq to dx should be the same as the overall ratio of charge to length of the bar. Okay, so dq dx, and what that's going to allow me to do is it's going to allow me to rewrite dq as lambda dx. Okay, so I'm going to go back up to my integral for the electric field, and that is EP is equal to the integral of all the little tiny electric fields from 0 to EP is equal to the integral of k dq, but I'm substituting in lambda dx over x squared. Okay, now that I've satisfied all the rules for beginning an integration, that is, everything's attached to a small factor, and the variables match the small factor that they're attached to, I'm going to go ahead and choose integration bounds here. I want to make this a definite integral. So I'm looking at, okay, at what x, at what position will this bar start contributing to the overall electric field, right? So anything from, well, this is my origin, so anything from 0 to D, there are no charges in that region, so nothing is contributing until I get to position D, and then continuing until I get to a position of here is D plus L, right? So I want to add up all the charges from D to D plus L. So my integration bounds are going to go from D to d plus L. I'm going to make this integral look a little bit simpler by pulling out all constants. So that's k lambda times the integral from d to d plus L, and I'm going to write 1 over x squared as x to the negative 2 dx. Okay, so that's an integral that I'm prepared to do. It's not a terrible integral. We're going to add 1 to the exponent, gives us x to the negative 1, and then we're going to divide by that exponent. So we end up with a negative out in front, negative k lambda x to the negative 1, or that is 1 over x. And I need to evaluate that guy from d to d plus L. But one thing I'm going to do, just a little trick, I'm going to take care of that negative by flipping my integration bounds or my boundary conditions. So I'm going to call this guy then k lambda over x from d plus L to d. And that takes care of the negative that was in front. So let's go ahead and evaluate this integral at d and then at d plus L. So this is the electric field at point P is equal to k lambda over d minus k lambda over d plus L. And I'd really like it if those denominators matched. So what I'm going to do is I'm going to go ahead and multiply by 1. And that is multiplying by a very clever 1. So over here I'm going to do d plus L over d plus L. Over here I'm going to multiply by d over d. And now finally my denominators match. So I should be able to go ahead and do this subtraction. So k lambda times the quantity d plus L all over d times d plus L minus k lambda d over d times d plus L. Okay? Since the denominators match, I'm going to go ahead and distribute the k lambda and then subtract k lambda d. So this guy becomes electric field at point P is k lambda d when I distribute plus k lambda L minus k lambda d, combining the two terms, and then writing the common denominator there, d times d plus L. Great. But I notice up here on top that two of these factors are the same, k lambda d and k lambda d, so they cancel, and I end up with an electric field that looks like this. Electric field at point P is k lambda L over d times d plus L. But I've got this lambda that I sort of made up, right? In terms of doing a free response question, lambda was never given in the original problem. It's something that I made up as the charge density, charge per length. So I need to go ahead and substitute back in for that lambda is Q over L. So my electric field becomes KQL over LD times D plus L. But the L's cancel, and I end up simply the electric field at point P is KQ over D times D plus L. Okay? Well, one thing that you're going to find that's really interesting now that we get to these continuous distributions is if you ever look at something from really, really far away, it just looks like a point, right? No matter what the shape of the object is, no matter how large it is, if you look at it from really, really far away, it just looks like a point. So what I'd like to do is I'd like to back away from this bar. I'd like to get really, really far away from it, and I'd like to see what the electric field looks like, and it's a good way of confirming that I've done things right. So if I get really far from this bar, that would be when D is much greater than the length of this bar. When D is really, really big, especially compared to the size of this bar. So what I'm going to look at is D much, much greater than L. And let's look at the electric field at point P if I'm really far from the bar. So what I want to do, if D is much bigger than L, then I'd really like to look at the ratio of L to D. And I'm going to do that by factoring out a D from this term in the denominator. So this electric field is KQ over D, but I'm pulling out another D. So that's going to be a D squared times 1 plus L over D, right? I pulled a D out of here, so I got 1 plus L over D. But if L is really small compared to D, then this ratio is essentially 0. And I can go ahead and distribute the D squared, and I come up with an electric field. And because of this assumption that I've made right here, calling that 0, I'm going to say the electric field is approximately KQ over d squared. And that's what I would expect when you look really, really far away from this distribution, that it basically looks like a point charge. When you're really far away, that object just looks like a dot, and the electric field you feel from that distribution is just kq over r squared, which is what we'd expect for a point charge. Okay. The next thing we're going to do is the next video, we'll go ahead and move that point P somewhere above the charge, and that one's going to get a little bit more complicated, but I definitely think you guys can do that one. So let's move on to that next video.